Okay, let's dive in. Imagine this. A single sentence, right? Hidden away in one of the oldest math books ever written, holding a key to how our universe actually works.
We're talking about Euclid's Elements. I mean, it's a monumental work. Only the Bible has seen more printings.
Incredible. And for what, over 2,000 years, it was the book for mathematics?
Absolutely, the foundation. But tucked inside its seemingly perfect logic was this one statement, a postulate, that caused trouble for centuries.
Yeah, the fifth postulate. It just felt off somehow. And mathematicians were uneasy about it for ages.
They were. It didn't quite seem to have that self-evident quality of the others.
But here's the twist, right? That feeling that maybe it was flawed, it wasn't a flaw at all.
Not at all. It turned out to be a doorway. A doorway to what one mathematician famously called strange new universes.
Strange new universes, which, almost unbelievably, we needed to understand our universe.
Which is the core question, isn't it? How does an abstract mathematical puzzle, debated for millennia, end up having such huge consequences for physics and cosmology?
That's exactly what we're exploring in this deep dive. We're tracing this incredible journey from ancient Greece right up to modern science.
And for those of you listening, perhaps preparing for the UPSC exams, this is a really fantastic case study. It shows how deep theoretical ideas, where science meets philosophy, can become incredibly important. Relevant for mains, maybe prelims too, but definitely great general knowledge.
Definitely. So let's go back, way back, around 300 BC, Euclid.
His ambition was just immense. He wanted to gather all the mathematical knowledge of his time into one single work, the Elements.
Like the ultimate math textbook of the ancient world.
Pretty much. And you need to understand the problem he was solving. Before Euclid, mathematical proofs could be, well, a bit messy. Lots of circular reasoning.
Right, where you accidentally assume the thing you're trying to prove.
Exactly. You end up chasing your tail, logically speaking. Euclid's genius was the axiomatic method.
Okay, break that down.
He basically said, let's start with things we absolutely know are true, or at least things we'll agree are true without proof. These are the postulates and common notions. And definitions, of course.
Like building blocks.
Precisely. Build the entire structure of mathematics logically from these foundations. No more circular arguments. It established a standard for rigor that, honestly, we still use today.
And the Elements itself, huge.
And massive. 13 books, 465 theorems, covered geometry, number theory, everything known back then.
And it all starts at those basic definitions in book one, like a point is that which has no part.
A line is a breathless length. Simple concepts trying to pin down the fundamentals.
A straight line is a line that lies evenly with the points on itself. Very intuitive.
Mm-hmm. And then come the first four postulates. These felt pretty solid, didn't they?
Yeah, totally. You can draw a straight line between 2 points.
You can extend a line indefinitely, sure.
Draw a circle with any center and radius. Makes sense.
And all right angles are equal. Seems obvious, right?
Completely. But then, postulate number 5.
Yes, the sticking point. It's wordy.
It really is. Let me try. If a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side. Phew.
Huh, exactly.
Yeah.
It's just so much longer and more complex than the first 4. It doesn't have that immediate aha feeling.
It feels less like a fundamental truth and more like something you should be able to prove from the others.
And that's precisely what people thought for centuries. Proclus, the ancient Greek philosopher, argued it was a theorem, not a postulate.
So the race was on to prove it.
For how long? Oh, hundreds and hundreds of years. Mathematicians like Ptolemy, Proclus himself, they all tried.
And failed.
Well, they thought they'd succeeded, but their proofs always ended up relying on some hidden assumption that was basically just another way of stating the fifth postulate itself.
So back to that circular reasoning problem.
Exactly. They were stuck, so they shifted tactics. They tried proof by contradiction.
Okay, remind us how that works.
You assume the opposite of what you want to prove. So assume the first 4 postulates are true, but the 5th one is false. Then you follow the logical steps from there.
And the goal is to find a contradiction, something impossible, like 2 + 2 = 5.
Precisely. If you reach a logical dead end, a contradiction, it means your initial assumption that the 5th was false must be wrong. Therefore, the 5th postulate must be true.
Okay, so what does it mean for the 5th postulate to be false? Euclid basically said there's only one parallel line through a point next to another line?
Right, so the alternatives are either there are no parallel lines or there's more than one.
The no parallels idea. That didn't last long, did it?
No, it seemed to conflict pretty directly with the second postulate that you can extend lines indefinitely. If all lines eventually meet, they can't be infinite in the way Euclid described.
Okay, so that leaves the other option.
Hmm.
More than one parallel line through a point.
And this is where things got really weird.
Yeah.
Mathematicians assumed this was true, multiple parallels, and then tried desperately to find that logical contradiction.
For how long did they try this?
For over 2,000 years, they explored the consequences of this multiple parallels world, searching for that one fatal flaw, that inconsistency.
And they found nothing.
Nothing. No contradiction emerged. It was baffling. They couldn't prove the fifth postulate, but they couldn't disprove it by assuming it was false either.
Just imagine the frustration. 2 millennia of brilliant minds hitting a wall.
It's incredible. Until the 19th century. Then things started to crack open. Independently from different places.
And one key figure was János Bolyai.
Yes, a young Hungarian mathematician. Around 1820, he got completely obsessed with this problem.
Didn't his father warn him off it?
He did. His father, also a mathematician, had wrestled with it himself and basically told János, "Don't go down that rabbit hole. It's a bottomless pit. It drove me mad."
But he didn't listen.
Thankfully, no. He kept pushing. And he arrived at this absolutely revolutionary thought. What if the fifth postulate isn't provable because it's just independent? What if it's an option?
Like you could choose whether it's true or not.
Exactly. What if you could build a perfectly consistent geometry where it wasn't true? Where you could have more than one parallel line?
But how does that even work visually? On a flat piece of paper, it seems impossible.
But geometry doesn't have to be flat. Think about curved surfaces. The shortest path between 2 points on a sphere, for example, isn't a straight line in the flat sense. It's a great circle.
Right, like lines of longitude on a globe.
Exactly. And on certain types of curved surfaces, like a saddle shape, what we call hyperbolic geometry, you can have multiple lines going through a point that will never meet another given line. They all curve away from each other.
So on these weird surfaces, the multiple parallels idea actually works.
It does. Think of a Pringles chip, or maybe a piece of crochet coral that gets all ruffled. Space itself in this geometry sort of expands exponentially. It's wild.
And Bolyai figured this out without even having these models.
That's the amazing part. He worked it out purely through logic before visual models like the Poincare disk, which maps this infinite hyperbolic plane onto a finite circle, were developed.
Wow. No wonder he was excited.
He was ecstatic. In 1823, he wrote to his father saying, "Out of nothing, I've created a strange new universe." Just captures the sheer breakthrough, doesn't it? Building consistent math by tossing out something everyone thought was essential.
A strange new universe indeed. Now, Bolyai wasn't just a math nerd, was he?
Huh. No, quite the character. Army officer, apparently a brilliant violinist, and yeah, the legend says he once fought and won duels against 13 opponents consecutively.
Okay, that's impressive. But back to the math, he published his findings.
He did, eventually, as an appendix to his father's book in 1832. And he sent it to the top mathematician of the day, Carl Friedrich Gauss.
The prince of mathematicians. What did Gauss think?
Gauss's reply was a bit of a shock for Bolyai. Gauss praised the work, called it brilliant, but then dropped the bombshell that he'd actually discovered the same things himself decades earlier.
Ouch. Decades. Why didn't Gauss publish?
He admitted privately he was afraid of the backlash, the clamor of the Boeotians, he called it basically, afraid of being ridiculed by less insightful people for proposing such a radical idea.
So Gauss knew about non-Euclidean geometry. He even named it that, right?
He did. He'd explored the consequences, like triangles having angles that sum to less than 180 degrees, or shapes with infinite sides but finite area, things that make sense in that hyperbolic model. But he kept it quiet.
Wow. And we should also mention the other non-Euclidean case, right? Spherical geometry.
Absolutely. On the surface of a sphere, the no parallels option actually works, in a sense.
Because any two straight lines, great circles, eventually intersect.
Exactly. They always intersect at 2 points. So no parallels are possible. This also violates Euclid's fifth postulate, but in the opposite way to hyperbolic geometry.
And Gauss, being a master surveyor, mapping the Earth, he would have known spherical geometry inside out.
Definitely. There's even speculation, probably unfounded, that he tried measuring angles between mountaintops to see if real space deviated from flatness, but the scale was just too small.
So how did Bolyai take Gauss's news?
He was devastated, crushed, really. Felt Gauss was trying to steal his glory. He became quite bitter and sadly never published any more mathematics.
And wasn't there someone else too, a Lobachevsky?
Yes, Nikolai Lobachevsky, a Russian mathematician. He'd also independently discovered and published on non-Euclidean geometry even before Bolyai's appendix appeared. A classic case of simultaneous discovery.
What a story. Though Gauss, privately at least, recognized Bolyai's brilliance.
Oh, yes. Despite the controversy, Gauss privately called Bolyai a genius of the first order.
So the ideas were out there even if the discoverers had a rough time. But spherical geometry wasn't quite fully accepted initially.
Right, because on a sphere, lines aren't infinite, they loop back. Bernhard Riemann in 1854 really generalized the whole concept.
How so?
He tweaked the second postulate. Instead of infinite lines, he talked about unbounded lines. That neatly brought spherical geometry into the fold. But he went much further.
Further how?
Riemann developed the mathematics for geometries where curvature could change from place to place, even in higher dimensions. This was incredibly powerful and abstract.
And then came the proof that these weren't just mathematical games.
Exactly. Eugenio Beltrami in 1868 rigorously proved that these non-Euclidean geometries were just as logically consistent as Euclid's geometry. If Euclidean geometry was free of contradictions, then so were these strange new universes. They were mathematically sound.
Which is mind-blowing. And then physics catches up.
Astonishingly, yes. Fast forward to the early 20th century. Albert Einstein. His special theory of relativity had shown space and time were intertwined, relative.
And that caused problems for Newton's theory of gravity, which assumed fixed space and instant action at a distance.
Big problems. Einstein needed a new theory of gravity. And then he had his happiest thought.
A falling man.
A falling man. Realizing someone in free fall feels weightless, just like someone floating in space.
Meaning gravity isn't really a force pulling things?
Exactly. Einstein's leap was realizing that mass and energy don't create a force. They actually warp or curve the fabric of space-time itself.
And things moving through space-time just follow the straightest possible path in that curved landscape.
Precisely. They follow geodesics, just like Bolyai's lines on curved surfaces. We see an orbit is curved, but the object itself is just following the straightest path available in the curved space-time created by, say, the Earth.
Like the space station falling around Earth.
That's the perfect image. It's constantly falling along a geodesic.
And we can actually see this curvature.
Oh, absolutely. Gravitational lensing is a prime example. We've seen light from a distant supernova bent by a massive galaxy in between, making the supernova appear in multiple images.
Didn't they even see a replay of one?
They did. Predicted it and saw it later, as light took a longer path through the warped spacetime. Incredible confirmation.
And gravitational waves.
Even more direct evidence. Those ripples in spacetime, detected from merging black holes and neutron stars. It's direct proof that spacetime can be disturbed and curved. The nanograv results hinting at a background hum add to that picture.
So at the heart of general relativity, our best theory of gravity
is the non-Euclidean geometry of Bolyai, and especially Riemann. Those abstract mathematical ideas turned out to be the language needed to describe gravity and the cosmos.
Amazing. So if spacetime is curved locally, what about the universe as a whole? Does it have an overall shape?
That's the big question. Just like triangles have different angle sums on flat, spherical, or hyperbolic surfaces, we can look for similar effects on the largest scales imaginable.
A cosmic triangle. But how do you measure that? Gauss couldn't do it with mountains.
We need something much, much bigger. We use the cosmic microwave background, the CMB.
The afterglow of the Big Bang. The oldest light in the universe.
Exactly. It fills the entire sky. And it has tiny temperature variations, little hot and cold spots, left over from the very early universe.
And these spots form the corners of our cosmic triangle.
Effectively, yes. How big those spots appear to us depends on the overall geometry of the universe the light has traveled through. If the universe is flat, they appear a certain size. If it's curved like a sphere, closed, they'd look larger. If it's hyperbolic, open, they'd look smaller.
So we look at the distribution of spot sizes, the power spectrum.
Precisely. And the data, especially from the Planck satellite, is incredibly precise.
The result.
Astonishingly flat. Within a tiny fraction of a percent error, the universe appears to have Euclidean, flat geometry on the largest scales.
Flat, after all that talk of curvature.
Locally, space-time is definitely curved by mass and energy. But overall, the average curvature seems to be zero. It means the universe's total energy density is incredibly close to this critical density needed for flatness.
Which is weird. Lucky.
It's one of the big puzzles in cosmology, often called the flatness problem. Why is it so precisely balanced? Inflation theory offers a potential explanation, but still an active area of research.
So we went from one awkward sentence in Euclid.
Through centuries of doubt, the invention of entirely new geometry is thought to be purely abstract.
To Einstein realizing that curved geometry is gravity.
And finally, measuring the universe itself, finding it's flat. Overall, what a journey.
It really is. And the key takeaway, especially thinking about, the kind of critical thinking needed for UPSC or just understanding the world, it's the power of questioning assumptions.
Absolutely. For 2,000 years, the fifth postulate was treated as something that must be provable from the others. It took radicals like Bolyai, Lobachevsky, Gauss, Riemann to say, what if it's not? What happens then?
And exploring that what if completely changed mathematics and then physics. It shows how vital that abstract foundational thinking can be, leading to totally unexpected real-world applications. You see this connection across science and philosophy.
Exactly. That willingness to explore seemingly impossible ideas is where breakthroughs happen.
And it leaves us pondering, doesn't it? If the universe is so remarkably flat overall, why? What does that tell us about the Big Bang or fundamental physics? And are there other, maybe more subtle geometric secrets hiding in the cosmos?
Could there be other strange new universes hidden in the math or physics yet to be uncovered? These questions are what keep science moving forward.
Definitely food for thought. Now, we'd love to know what you think. Did this journey from Euclid to Einstein spark any questions for you?
What aspects surprised you the most? Let us know.
Please do like and subscribe to The Deep Dive if you enjoyed this exploration. We'll be back with more deep dives into crucial topics.
And definitely leave a comment below. Any further queries, thoughts, or connections you made, we really value hearing your perspective.